Okay, in this video we're going to be studying ray traces for lenses in particular. So I'm going to introduce you also to the three main principal rays. Those are going to be useful in the lens video for ray tracing as well as the mirror video for ray tracing. So you'll need to pay attention closely to the three principal rays. Let's look at the basic idea first, okay? We're also going to check these with our equations, but the basic idea here, let's start off with a convex lens, so just a positive lens, okay? Okay, and I want to set up a measurement system here as well. So we'll remove this ruler when it's time, but we have the optical plane set up at the 12 centimeter mark, and then we can place any of our objects, images, or the focal length at any point that we need to here. So remember that the optical plane is the basis for measurements for your P and Q. So we're going to place an object here at 8 centimeters from the location of the lens. So we'll be writing it right here at the 4 mark. Will be where our object is placed. And I'd like to have a focal length on this thing at 4 centimeters away. So we can write these down now as a focal length of positive 4 centimeters and an object distance, P, of positive 8 centimeters. Don't forget that that P is always positive, right? And our objective will be to find where the image location is, but the way that we're going to go about doing this is by ray tracing. Okay, let's place our object. So I'm going to make it about this tall. And we won't put a number to it, but we'll be able to visualize how tall it is whenever we find our image location. So without running through the equation, we can find this by using three principal rays. The first ray, I named the first ray a parallel to focal ray. The second ray, I name a center ray. These won't be these will be similar to the principal rays that you'll find in the book, but the way that I name them here will hopefully guide you to do your ray tracings without mistakes. So the third one will be the focal to parallel. Okay. Let's keep these individually color-coded. So we'll make the parallel to focal a green ray, we'll make the center ray a blue ray, and we'll make the focal to parallel a purple ray. Okay, so parallel to focal, remember that when I say parallel, I mean parallel to the optical axis, so that's the way we're going to go about this. Now first off, we have a focal point here, but we need another one over on the other side. Okay, so we take from the tip of the object a parallel ray, and when it encounters the optical plane, it will be focused toward the focal point. Okay, that's our first ray. The second one is called the center ray. The center ray is actually a very easy one because all you have to do is take it from the tip of the object directly through the absolute center of the system. So right where the optical plane and the optical axis meet, right? Okay, so that ray. And the third ray is our focal to parallel ray. Again, you start off at the tip of the object, but this time we go through, we've already used up this focus over here. So we don't need that one anymore. We need to use this one. So we go through this focal point, and then when we encounter the optical plane, then that will cause this to go parallel. Now, how do we know that? Well, we know that because if we sent this parallel ray in this side, it would go to this focal point. So we're using that knowledge to our advantage to backtrace it from the object to find out where all these would go. Now, these aren't the only rays that are going through the lens, but they sure are three easy ways to figure out the locations of and the ultimate, the trajectory of. So you can see that they all meet at the same point. It won't always meet exactly at the same point. Sometimes your measurements will be a little bit off, and you'll end up with this sort of little triangle here where each ray is sort of meeting a little bit off of one another. But it is a really good estimate, and we should be able to take this, draw our image corresponding. So we'll draw our image in gray here. There's the tip of the image. And I guess I shouldn't make it look bigger than it is. And we can actually compare that using our equation now. So remember your equation, lens maker equation. We're solving for Q, and just like in the previous videos, that should give us 1 over F minus 1 over P flipped, or 1 over 4 minus 1 over 8 flipped, which gives us, that's the same as 2 over 8 minus 1 over 8, so that should give us 1 over 8 flipped, or 8 centimeters. So our Q is a positive 8 centimeters. Remember that in the lens case, positive means that the light has gone through and the image formed on the other side. We can also see the magnification is going to be negative Q over P, which gives us negative 8 centimeters over, and our object distance P was positive 8 centimeters. So that means we have a magnification of negative 1. In other words, it's the same exact size, but it's flipped. It's flipped upside down. So let's take a look at our ruler and see how close we were. So not perfect, but we did pretty good. This is 4 centimeters, 8 centimeters. We landed on the 8.5 centimeter mark, so that's not too bad. But it did give us a pretty decent estimate. I don't want you to feel like you have to have it super accurate on these ray traces. Try your best. I mean, we were pretty clean and careful on this particular problem, but if you end up with something way down here, then obviously you did something wrong, right? So this is good enough as far as ray tracing is concerned. Okay, now we tried a convex lens, or positive lens, and we tried it such that the object was located way out here and the focal point is way here. Let's see what happens or how it changes if we move the object inside the focal length. Okay, so I've located my object now halfway to the focal point, which means that it's settled at 2 centimeters. Let's double check that. See here, you can see it's 2 centimeters away from the optical plane. Now we can go about our process of ray tracing again. Let's remember what our 3 principal rays are. We have a focal to parallel, or parallel to focal, excuse me. And by parallel, sometimes I'll refer to this as infinite to focal, and the reason is because it comes in infinitely far away, it remains parallel the entire time. So parallel to focal. and then center array, and then focal to parallel. Now, we have to be careful here. This is one type of problem that students have a tendency to get a little bit tripped up on. The first one is going to be fine. We'll color code these so that we have the first one in green, the second one in blue, and the third one in purple. So the green one's not going to be too bad. Again, we have a parallel ray that when it strikes the optical plane goes to the focal point on the other side. And we can draw our arrows to make sure we're clear about direction of the physical direction of ray travel there. Let's move on to the center ray. Center ray is also not too bad. So we go directly from the tip of the object through the center. And again, make sure to indicate directionality there. It's this third one that tends to trip people up. This is the purple focal to parallel. Now, recall that we've already used this focal point over here, right? So we need to use this one, but we can't draw a ray from here. Well, I shouldn't say we can. We can draw a ray from here to there, but that's not very useful because it never encounters the lens, right? But what if we instead drew a ray that goes to this point from the focal point? So let's pull out our guide, our straight edge here, so that we can put that on the focal point and go exactly to the tip of this thing. And then what we're doing is we're showing a ray that's coming from the same direction that a ray would come from if it came from this focal point. Okay. Then we can create a parallel ray. So we are going actually focal to parallel. We just didn't actually come from the focus. We instead came from a point that was along the line of the focus. Okay. Again, remember directionality. Okay. So now you might see an issue here. You might see an issue. These aren't meeting. In the last one, we saw that the lines, the rays met, and we knew that the image was in the location where they met. This time, what we're seeing is that they appear to meet. So what we'll do is we'll take our ruler and locate the ruler on this ray here, and we're going to trace that ray back to where it appears to come from. Let's use a little bit of a lighter and dashed line. I like to use dashed lines for these because they're not real, they're just apparent rays. So let me do that again with the green here. So we have a ray that appears to be coming along this line. And that's not very bright. Let me see if I can get that a little bit darker. There we go. Okay. And we also will have one coming from this blue ray, so let's make sure that we're tracing that as well as possible. Now, we really should take a look here at where these appear to be meeting. Two of them, the blue and the green, appear to meet here. The green and the purple appear to meet here, and the blue and the purple appear to meet here. Like I told you before, that creates this little triangle of possibility where our image could be located. So let's go ahead and take, sort of a rough average there and place our image in that spot. That's the tip of the image, so we would expect it to look something like this, because it has to go to the optical axis, It appears to be much larger than the object. And so now let's run our equation and see if we can get the same, or roughly the same answer. But before we do that, let's take a look at intuitively why is this here? Don't forget these rays when they come through the lens. The eye does not know where the ray came from. It only knows where the rays appear to come from. So this purple ray, your eye is tricked into thinking it came from this direction. The green ray, your eye is tricked into thinking it came from this direction. They appear to have originated at this point. That's why we have this image formation. Now let's run our equations and see if we get anything close to that. We'll go through the same process again, and remember Q was 1 over F minus 1 over P to the negative 1. And that's going to be, in this case, remember the focal point is still 4 centimeters. And P, in this case, is 2 centimeters. So that gives us 1 over 4 minus 2 over 4, or negative 1/4. We flip that, and we get negative 4 centimeters. So our image distance is negative. Remember, this is a lens. So we expect light to go through the lens, and if the image forms on the opposite side, then it's negative. So we do appear to be on the correct side. And let's get out the ruler again, see if that matches. Not perfect, just like the last time we were off a little bit. But within a half a centimeter here, we're about right. So it actually should have fallen right here on this focal point. Now, what is this device? If you think about it, then you'd probably be able to identify this. This is a device that tricks your eyes into thinking that something is bigger than it is. So you actually see a bigger image than the object itself is. That's a magnifying glass. This is set up just like a magnifying glass. The object in this case might be letters on a page or something like that. So if you get the magnifying glass close enough to the letters on the page, it begins to magnify them. If you start to move the magnifying glass away from the object or the page, in the case of reading a book, it would be a page. If you begin to move it far enough away so that the focal point comes with your magnifying glass and keeps on moving to the right until the object is then out of the focal length, then you will note from our last retrace that it flips upside down. And so if you actually do that with a magnifying glass, you'll see that happen. If you get far enough away from a book, it'll flip upside down and it'll change the sizing. So, okay, let's try again, but this time we're going to use a diverging lens or a negative lens. Okay, so we have the case of a diverging lens or a concave lens or negative lens. We can see now that we're going to need to put the focal length as a negative number. And it's still 4 centimeters, but it's negative this time. So our object distance is now, instead of 8 centimeters, is at the 6 centimeter mark. So I can go ahead and put these numbers in, but I'm not going to calculate it this time. So I just want to make sure we understand how to do this ray trace. Now I've written down here, remember our three principal rays, the parallel to focal, center ray, and the focal to parallel. And you have to think very carefully through each one of these. Now, don't get tripped up by the way that this lens operates differently than the other lens. Just remember, when you get a lens like this, that its entire job is to get rays to spread out, not to get them to focus. So we'll begin with our parallel to focal, but don't be misled by the term parallel to focal, because essentially what we're doing here is, instead of going parallel toward this focal point on the other side, we're actually going to be diverging away from the focal point. In which direction? Well, let's put this on this focal point, and our ray will actually be diverging away, pointing away from this focal point. Okay, so that's parallel on this side, and it's focus oriented on this side, but we're using this focal point instead of this one. Now, how do I know that? Because there's no way to use this one over here, because I would have to bend toward the optical axis instead of away. The center ray, luckily, nothing has changed here. The center ray is still just that same old boring right through the center. Now, what about the focal to parallel ray? Again, think carefully. We have already used up this focal point. We now need to use this focal point. We can't go directly across. That's not going to do us any good. What if we pointed a ray at this focal point? If we point our ray at the focal point, what would happen when it hits the optical plane? It should go to parallel, like so. So, indicate direction. Now, thinking in terms of what we did with the last lens, we can see that the rays appear to be coming from a different direction than they're actually coming from. So we've got this sort of trickster system going on again. If we trace this back, then the direction this one appears to be coming from looks like that. If we trace the green ray back, then it looks like it's coming from this direction. And then the blue ray actually does trace back by itself, so we don't have to worry about that. So they meet right about there. So we would expect our image to be located here. If you run through your calculations with a negative focal point, you'll find that that is roughly the place where that would be. Okay, so this is 3 examples to show you how to use the 3 principal rays. In the next video, we're going to be doing the same thing with our spherical mirrors, and we're going to be using these same 3 rays. So, see you there.